we'll use the code we already have here. So we'll create a variable here, maybe int cost, and we're just going to come up with some sort of cost for something. So let's say this is $14.28. So it'd be like $14.28, that type of thing. And then we're going to say int payment is equal to, let's say we give them 2,000, so $20 to pay for the $14 thing. So I said give it to them in pennies, right? All right, so then we're going to have another variable here, maybe called change, and change is going to be payment minus cost. So that's the thing that we need to give change for, right? All right, so now I have my, effectively what I want to do is I want to show dollars, quarters, dimes, nickels, pennies for whatever changes, which is going to be 2,000 minus 14.28. So 572. So this should be $5, 2 quarters, a dime, no, 2 dimes, right? And 2 pennies, 0 nickels. All right, so let's go ahead and let's go ahead and display this. And I said solve this in terms of the things you learned about in class so far. So we're going to spit stuff out to the screen. So the first thing we need to do is we're going to show them dollars. So we're going to say cout, say something like dollars like that. And then we need to give them dollars is going to be change divided by 100. So if my change is 572, 572 divided by 100 is 5, right? So it's no decimal point or anything because we're doing integer division. All right, now that I've printed out the number of dollars, I need to adjust my change to be less than it used to be. All right, so I'm going to set change equal to. So now what I need to do is I need to whittle change down to, ultimately in this case, it's going to be 72 cents. Right? All right, so change is going to be equal to whatever change is currently equal to, which is the 572 in our current example, minus change divided by 100 times 100. That'd be good enough. It'll get the job done. So 528 divided by 100 is 5 times 100 is 500. So now we'll have, what was it, 572, I think it was. So we'll have 572 minus 500, which will give us 72. So just to test that real quick, I'd maybe take a little break. And I was going to print out change real quick because we want to make sure change currently says 72 in this example. So there's my dollars is 5. And now we've kind of confirmed for us that we're whittling it down the right way. Make some sense? All right. So I didn't solve the whole problem immediately. I took a little pit stop and just made sure that my math was right. All right, before I got too deep into it. All right, so now I pretty much know I have the right cadence here. So I'm going to steal those couple of lines. So next thing we're doing is quarters. And quarters is going to be change divided by 25. All right, so that should give us 2 quarters, right? Go ahead and run this. So there's our 2 quarters. All right, then we want dimes. Change divided by 10. Now don't get confused on this part here. Like, why am I dividing by 10 and then immediately multiplying by 10? Remember that this is integer division. So we're losing any decimal point stuff there. So when I divide by 10 and then multiply by 10, I don't necessarily get the original value of change. because I've lost potentially some precision here when I took change and divided it by 10. If it was 3.72 or something like that, that 7.2 is gone for the moment. All right. Then we have nickels. And that's 5, 5, 5. And there are several different ways you could have accomplished this kind of mathy. You could have created multiple variables for each of these. All that's fine. And then pennies. 1. Really, actually, I don't need to even divide it anymore. Now it's just whatever's left over, right? Change. That's my leftover stuff. So there's my $5, 2 quarters, 2 dimes, 0 nickels, 2 pennies. All right, so now I've written this logic. So now if I go up and I just change my cost to be $27.81, and I give them $50, I'll get a different answer. So I didn't have to change any of my other logic. I just changed what the inputs were. Make some sense? All right, questions about that? Go ahead. Where are we talking about? Well, you oh, yeah. Right. You can't. Yeah, this was, I was wanting to show what the integer division loses precision, but you're right. Yeah, you could have done this in a little bit shorter way. Okay. So let's call that a reasonable way of going about it. Go ahead. Yeah, well, so something you're doing in here is not the same math as I'm doing. So, I mean, we can look at it closer if you want to bring it up after class or something, but I'm sure there's some little thing you're doing. It's not that your interpreter is off or something. All right. So just as a quick addition thing here, let me go ahead and show you how to read stuff in from the user. Again, modernly, this isn't something that happens all that often. Because now a lot of times you'll have like a little text box, you type some stuff in, hit a submit button, and that's how you get your stuff to your programs. But historically, we did a lot of command line stuff. We would have read stuff in from the user. So just as C out is the way we write stuff out to the user, C in is how we get stuff from the user. All right. So I'm going to do something like C out, enter the cost. Put a little space here. Now I'm purposely not pressing enter after this line. So I'm not doing that end L thing. That way it's asking me for the cost and then just sitting there waiting for me to type something in. So I'll define my variable cost and then I'll say C in the cost. And we'll say C out, enter the payment. We have hit payment, so I'm defining the variable so it exists, and then I'll read in to that variable. So enter the cost, 27.21, and I'll give them that. And there's my answer. So I just changed the way we're reading in from the user. Rather than me hard coding a value for cost and for payment, I asked, I prompted the user, which you don't have to prompt them, but otherwise the user doesn't know you're asking them for anything. If I leave that line out, then the beginning of this program is just going to be sitting there and it's waiting for you to do something. You can do it. No, it finally did it, but there. So right now my program looks like it's not working, but it is. I just didn't actually give them any output asking them for something. It's waiting for me to give them the cost. So I can type something in and now it's waiting for my, I may have actually broke it here because I pressed enter. Oh no, it waited for it. All right, go ahead. Because yeah, when I said CN, I'm setting whatever I'm reading in, toss into this variable. Well, so when let me put the prompt here. So this is me writing something out to the screen. Program doesn't care about that. That's human eyes, right? Then I'm defining a place to remember the cost. So now this variable exists and it's built for holding an int, but nothing's in there yet. Okay. Right here, when I say CN reads something in from the user. And I'm telling it whatever the user types, put into this variable. So from this point forward, so after line 17, costs will hold an integer. C++ is automatically converting it to the right type for you. It's holding an integer inside that variable called cost. So this is the same thing as what I had before when I said int cost is equal to 2711, something like that. From this point forward, cost now has a value being remembered inside of it. Just instead of me hard coding it here, I'm now prompting the user for it. This isn't necessarily better. Sometimes hard coding a value allows you to test more quickly. Because imagine if you're testing this thing 50 times, you might have a situation where it's, you're having to give it input every single time. And there's a lot of interaction between you and the program. It might take some time. In a program like this, we might choose to maybe generate random numbers and then, have it give us, our answers in dollars, quarters, nickels, yada, yada, yada. All right. So now what we know how to do is we know how to read something in from the user if that was beneficial for us in our program. Okay. So questions about this? Go ahead. Well, no, you should have already submitted your homework before class started. So this is more just the solution for your own records to learn from it, whatever. Yeah, because like I said, there's different ways you could have written this. In fact, like he pointed out, there's a shorter way of writing this in here, but it doesn't emphasize this idea of you lost precision there. That's why I wrote it like this. But shorter isn't necessarily better. In fact, a lot of times with beginning programmers, I suggest that you spell things out, do it in a mathy way that makes sense to you rather than taking some sort of shortcut that mathematically might be smarter, better, yada, yada, yada. But if you don't understand it well, you're not doing yourself any favors. Nobody's going to sit there and count the number of lines your program has and saying, oh, well, this was in 7 lines. Yours took 14. You suck. It's not the way it works. Every blue moon, you might be in an industry where you do need to write the most concise code possible because you're very limited on memory. But by the time you are maybe in a career path that uses that, it's not going to be a problem. All the stuff will make sense to you. You'll be able to write it more concise if you have to. All right. So questions about this? And what I'll do is I'll just copy that code real quick. Let me go to our 200 channel. Have it at the top. And let's see, is this the guy? Code block. So I just put my code up on Slack. You wanted to mess with it or whatever, if you're having a lot of errors in yours. Okay, so hopefully you're seeing, since you like you mentioned, you're getting a lot of errors. Several of you, I'm guessing, probably got plenty of errors when you were going through this, forgot semicolons, you were grasping at straws, whatever it was. That's normal. It's normal when you're first starting. All right, which is why I have you do the self-assessment, for you to have the opportunity to tell me I spent 4 hours on this and I have squat to show for it. All right, it's the point, because this is practice for the big game. I'll find out if you're learning the stuff when we hit the midterm, when we hit the final, because ultimately my job is to give you a grade based on how well you've mastered the material by the end of the semester. Cool. All right, so let's keep trucking here. All right, so at this point, we've kind of done a homework assignment dealing with memory, dealing with remembering some stuff. We have introduced the idea of a Boolean expression. What's a Boolean expression again? Any expression that boils down to a single value of true or false. You probably should repeat that to yourself 10, 20 times before you go to bed every single night. Something like that. Then maybe recite the Hello World program. It's like well, I mean, you could do it after that. It's less important, but it's up there. Is what I'm saying. All right. So let's see. So I gave you some example crap. Blah, blah, blah. We talked about Boolean expressions. Man, I'm all over the stuff with these slides, right? Yeah, it's awesome. That's got to be super hard to follow. Man, I'm glad that's not my problem. This is so good. All right, so Boolean expressions, talked about that. We introduced the arithmetic Boolean operators, a majority of which you're already familiar with from your algebra classes or whatever. The couple of new ones here are like this little exclamation point equal sign that's not equal to. In this language, there's some languages that do that with like two angle brackets facing each other. But in most C-based languages, it's the exclamation point equal sign. Okay, then we have the equivalence operator, double equal sign, not to be confused with the assignment operator, which is a single equal sign. We use the assignment operator to assign a value on the right to the variable on the left. That's what we use this assignment operator for. Make sense? So common mistake for beginning programmers is messing up by saying, oh, is something equal to, oh man, if that thing explodes and I go down, you take over. Okay, so you're up. This guy's always got he's temperamental. He just needs it. He's got a caffeine addiction. I've done it before. It has come on. All right. It's IT wiring stuff. Hitting the power button. It doesn't even want to die. Oh, there we go. That guy another shot. Is it doing stuff? Oh yeah, it's working. All right, that's as good as it's going to get right there. So if it starts doing it again, we're just going to suck it up. All right, so double equal sign is the equivalence, Boolean equivalence operator, as opposed to the single equal sign, which is the assignment operator. C++ will be happy to scream at you. More modern language will scream at you better. Okay, it's kind of more the reason we choose C++ in here, because it doesn't let you get away with much. which then makes it more frustrating to debug, which I know is torturous to you, but I promise you it'll be good for your future. Because everything else will be easy mode once you survive C++ and its cryptic or non-existent error messages, and you get your debugging skills up trying to fix stuff. Because Java or C#, some more modern languages, will give you a little bit more hand-holding, which you'll really appreciate later on. Okay, but right now we want to have the maximum level of torture to really haunt your dreams. All right. So those are our arithmetic Boolean operators. Then we had our logical Boolean operators. So this allows us to say things like and or. So ands are true whenever both things that were said are true. Ors are true if at least one thing is true. So if we say it's like today, it's sunny and warm, that's a false statement because it's not very warm out today, right? So it was kind of chilly. But if I said it's sunny or warm, which would be kind of a weird thing for a person to say, but technically it fits this example. Sunny or warm would be true because it is sunny out today. Pretty nice day out, all things considered. So that's the and the or thing. All right, so now let me show you a common mistake. So we're going to go ahead and just gut this stuff. Oh, Ninja. All right, so I'm going to go ahead and do a cout, and we're going to have a couple variables here. We'll say int a is equal to 7, int b is equal to 3. Go with that for a second. So we'll say we're going to cout a equal to b, or a less than 10. All right, first of all, is this a Boolean expression? Yep. Looks a little bit long, but it's technically, it boils down to a single value of true or false. So we break this down. Is a and b, are they the same number? Is 7 equal to 3? It's not, so that's false. Is 7 less than 10? It's true. So this is false or true. And since one of the sides, at least one of the sides is true, the whole thing will boil down to true. So there's our true. Remember, under the hood, Booleans are stored as numbers. A 1 is true, a 0 is false. Okay. If I change this to an and, now both sides need to be true for the entire thing to be true. So now it's a 0, it's false. Make sense? All right, so now I'm going to throw you a curveball. Is that a Boolean expression? Okay, you're right. What's the output of this going to be? I have purposely done something, let's call it erroneous. Okay. Okay, so first of all, what are we noticing is my possible mistake? Go ahead. Yeah, two ampersand things, right? Okay, so I've accidentally only put 1 ampersand instead of 2. So as far as right now goes, we're like, what the heck is that, right? Okay, now let's assume, just for a moment, let's assume I had put 2 and signs there. Is that a Boolean expression? No. Well, so why? What's a equal to? 7. What's b equal to? Okay, so 7 and 3. What does that even mean? Yeah, that's a meaningless thing, right? That doesn't make any sense. So I'll go ahead and hit run. Okay. It's doing something with the numbers under the hood. Java would have screamed at you. Okay. But now let me show you something interesting. Okay, well, let me explain why that is. I made a statement earlier that a 0 is false and a 1 is true, correct? It's actually not entirely accurate. The truth is that a 0 is false and anything other than 0 is true. So why did this come out to true? Because this is something other than 0 and something other than 0. You would never write this. This is like, okay, what are you trying to say here, right? But technically you get an answer from this. Make some sense? All right. So now if I go back to this, what do we don't know what we're expecting the result to be, right? And of course we get a 3. Why? Anybody know why we get a 3 there? Go ahead. The question is what is that, dude? Clearly it's not an illegal symbol because C++ was cool with it, right? All right. Now, what I'm going to show you here is not something I'm going to test you on. But the reason I'm showing you is actually is going to be something that might be beneficial next semester when you're in the 325 class. But really what I'm going to show you is for you to understand when you type something, we're going to say erroneously here. This isn't what we meant to do, but it's what we typed, right? We're not used to typing things or catching our own mistakes when we're doing it. But all of a sudden we get a freaky deaky output. And we're like, okay, well, why is 7 ampersand single ampersand B? Why is that a 3? That doesn't make any sense. And it's because we have these things. Let me just see where I'm going with these. I'm going to go right before the if statements. We'll just go right here. We have things called bitwise operators. So this is a bitwise and. This is a bitwise or. And this is a bitwise XOR, which is exclusive or. Exclusive or means one or the other, but not both. So when we've talked about ORs in general, we've said that an OR is if at least one side is true, the whole thing is true. An exclusive OR says exactly one side is true. If both are true, it's false. If neither are true, it's false. It has to be one or the other, but not both. That's what exclusive OR means. It's not something you'll probably use very often, but that's just what that extra guy is. It's why I don't show that is one of our common logical operators. Our 2 logical operators you'll actually use are double ampersand for logical and double vertical bar for logical or. These guys are bitwise operators. These are actually math operations, not Boolean operations, even though they're using our symbols for Boolean stuff. Okay. This is the exclusive deal. So double caret is actually exclusive or yeah, but nobody's going to, you can build it with ands and ors, normal ands and ors. I would just tuck that away as kind of trivia knowledge. I'm not going to test you on it or something like that, but there is a such thing as a exclusive or. When you get into the 325 class next semester, the computer organization class, where you start talking about hardware stuff. And this maybe goes hand in hand with news. If you listen to Geek News, you've heard things like chip shortages and stuff like that with why some of our technology is getting too expensive, whatever. We have all these different little tiny chips. These are called logic gates that are in short supply. And when you're like a big company like Apple or something like that, you can build any of these, a lot of these things out of other things. So you can get the equivalent output for several of these things by using a combination of other things. So what these big companies typically do is they'll buy a bazillion, which is an official number, by the way. So they'll buy a whole bunch of like NAND gates. A NAND gate is a not and gate. Or they'll buy a whole bunch of NOR gates, not or a whole bunch of XOR gates, XOR gates. And they'll buy a zillion of those and then use them in certain combinations to get the same output, because buying in bulk lowers their costs, something like that. Okay, so when they talk about chip shortages, they're typically talking about things like that, a subcomponent of our microprocessors or that kind of stuff. Unimportant for this class, but just more of a trivia knowledge thing. But these bitwise operators, I'm going to go ahead and put, these are math operations. I'm going to call them bitwise math operations. All right. Anybody know what I mean when I say bitwise? My expectation is probably you won't, but figured I'd ask. Okay, so let's look at this. We've seen an example here of 7 and 3 giving us a 3. If I go ahead and change this to an OR, we get a 7. If I change this to an XOR, we get a 4. Super useful stuff, right? All right, so let's look at why this works this way. So example, okay, and again, this is not something you're gonna maybe even ever use in your career, but it's something you might see during your career if you make a typo. Because instead of the compiler screaming at you, you're gonna all of a sudden get an output and you're like, well, what the heck is that? All right, so we saw that 7 and 3 gave us a 3. We saw a 7 or 3 gave us a 7. And we saw a 7 XOR 3 gave us a 4. Okay, so now we want to understand why this happened. Okay, what we're going to do is we're going to write the binary version of these numbers. So in binary, what's a 7? How do you write the number 7 in binary? That guy? That's a 7. All right. And how do you write a 3 in binary? That guy? All right. So we can all agree that this is the binary version of the decimal number 7. And this is the binary version of the decimal number 3. All right. We've learned the conversion stuff, so you can trust me that these are correct. I picked little numbers like this because this is like, remember our shortcut from octal? You can represent all of the octets using 3 bits. So a 7 is 111, a 0 is 000, and everything in between covers the 1 through 6. Okay. So we have 111 and 011, and this is the bitwise AND operator. And what we mean by bitwise is we do this operation on each individual set of bits. So we're going to take this first 1 here, and we're going to bitwise AND it with a 0. 1 and 0 gives me what? So what's a 1? A 1 is a true, a 0 is a false. True and false gives me what? False, because both sides need to be true, right? So that's a false. Okay. 1 and 1. True and true is what? True. True and true is what? True. What's 011? That's the number 3. That's where that 3 came from. Just steal this line here. So now we're going to change this to the OR. So So true or false is what? True. True or true is what? True. True or true is what? True. There's our 7. All right. So now we have our XOR. XOR is exclusive OR. It's only true if exactly one of the sides is true. If they're either both true or they're both false, it's false. So 1 XOR 0 is, so true XOR false is what? True. True XOR true is what? False. True XOR true is false. There's our 4. Right, that makes sense where those values came from. Now, none of us should necessarily be thinking, coming up with like, okay, that makes sense. I'm going to use that all the time. Probably for us right now, it's like, okay, well, I would never do that. I don't know why I would do that, but for us right now, it's, that's why I get the strange outputs. The outputs are calculable and they make sense in terms of why that's the answer. I don't know why I'd ever use that tool, but if I did, this is what I'd get. Make some sense? All right. You do use bitwise operations in a lot of encryption algorithms. So things that we're not necessarily writing in here, but things that deal with like a lot of kind of math tricks and stuff like that might use bitwise operations. So we do have a way in modern computer programming to represent these things, just not going to be very common for us. So my goal with showing you this in here is not something I'm going to test you over, but it's something that I want you to put somewhere in the back of your mind, because you're going to at some point make this mistake. We're going to use a single ampersand instead of a double ampersand, and instead of an error, you're going to get a thing. Okay, and you're more likely to get a thing with some of those errors in C++, like we saw a few minutes ago, where I did 2 different numbers. Remember, I did another example. I had the seven logical and 3. So I have a number followed by another number, and I said these are the Boolean operators. Well, technically, since Booleans are stored as numbers, this is a true and this is a true. Because in Boolean, in C++ and C, anything non-zero is treated as true. A 0 is treated as false. So even though my intention here is probably to create a couple of variables to do mathy stuff with, if I decide to use them in the context of a Boolean expression, C++ will be happy to treat them as Booleans, even though that was not my intention. In a language like Java, where it separates, same thing with C#, it disconnects us from the numeric side of Booleans. Okay, so in Java, this would be an error. Java would say, look, this guy's a 7, not a true false thingy. This guy's a 3, not a true false thingy. It's not going to treat that under the hood 7 as true. It's going to say that's a number, you don't know what you're doing, and it's going to scream. Well, in Java, you would write true or false. Yeah. Java hides it from you. So what I'm saying is when you're building Boolean expressions, our mind should immediately go to trues and falses. All right. The point is, and we can write this as trues and falses. We can say bool B is equal to true. Make sense? And I'm telling you that if we were to print out the math version of that, if I were to force B, so if I do C out B, in fact, I'm guessing it's going to give me numeric in this. This is going to, because I don't want to be, I want to see here. I had 2 variables named B. Don't do that. Only defined it once. Did it on purpose. Yeah, so we know that C is true, but when we wrote it out, we got a 1, which is true. In a language like Java or C#, this would have print out the word true. They disconnect for human beings. They disconnect that numeric way the values are actually being stored from the way that we should actually be thinking about it in terms of trues and falses. The reason we're using Booleans is because we want to be able to ask questions. We want to be able to say, if something is greater than something else, or if this is true and this is true, do something. We mean to think about these as trues and falses. We're just happening to see the evidence under the hood that C and C++ stores them as numerics. I'm promising you that in C#, in Java, in Swift, and every other programming language, under the hood, Booleans are being stored as numbers. But those modern languages decide, you know what? A human being is never going to mean to deal with these as numbers. They're never going to do math with a Boolean value. Therefore, we're going to, in software, make that disconnect. Yes, we are storing it numerically, but from the human's perspective, that's not their problem. It's a true false value. Don't do math at it or we'll scream. C and C++ won't scream because a number's a number. Make sense? So that means as a programmer, we need to understand the difference between how our values are represented inside the computer versus what we mean to do as a programmer. Right? And that kind of comes down to the idea I think I mentioned when you're working on your programs. Don't make changes unless you have a kind of at least an educated guess as to why you're making changes. Right? You don't want to solve your homework assignment by just trying every single permutation of stuff until it works. I'd much rather you make 100 logical guesses and get the wrong answer than make 30 random guesses and get the right answer. Because you're learning a whole lot with those wrong answers. Make some sense? Yeah, that's it. And the thing is, that's super common. We're looking at a pretty simple example here, but I mean, the point is that it's common for students to submit an assignment that does work, but you don't know why it works. And that's not going to hurt you in your assignment. You give me something that works, I'll give you your credit. What do I care? Right? I'm going to find out on the midterm that you don't know what you're doing because you've denied yourself of that practice. I grade homework easy because that's practice for the big game. You bomb the midterm, no problem. You're not screwed over yet. You can come back and do well in the final, and I'll replace what you got in the midterm with what you got in the final. Got lots and lots and lots of opportunities. Participate in practice to get better, not to just get the right answer. You're going to get your full credit regardless. Make sense? All right. Oh, sure. Oh, yeah, because they are numerics. Yeah. No. Well, other languages, there probably is other languages that do support that, but Java, no. C#, no. Swift, no. Oh, say Swift, maybe. There's probably some sort of technical true emoji or something like that you can use. Man, that would make me physically ill. Like a pink unicorn is technically a false or something like that. Funny thing is I'm not necessarily joking when it comes to Swift. That's ridiculous. And you can name variables with emojis.
I make it hard for like, I mean, it isn't like Swift, like iOS, like specifically.
Swift's like Java. Okay. Yeah, the whole purpose of Swift is to get Android programmers to come over and write iPhone stuff.
I see what writer.
Well, also reading it. Yeah. I mean, isn't that they had a whole movie about that, right? You had the parents sitting there and trying to read the messages from their kids that are all in emojis. What was that called? No, it was like the kids were creating like a sex pact or something like that for prom or so. But the parents are trying to figure out what the kids are saying with all the different emojis. You know, it's like a high school prom type thing where the parents are overprotective because they wanted the kids to behave themselves or whatever. We had these three crazy parents trying to read their text messages and seeing all these emojis and trying to figure out what all of it meant. You know, and it's pretty funny, but like we've reverted to hieroglyphics, right? You know, we're like these you know, these you know, people digging up Egyptian artifacts and trying to read the stones on the walls. You know, we're right back to throwing that inside of our programs. That doesn't make any sense. Whatever happened to Apple's Animojis? That was cool for 5 seconds. Yeah. Yeah, what is going on? Just it worked though. They sold a zillion of those things just on the Animoji stuff, and now their new phone has the island, the digital island they're calling it. Yeah, that top little, the notch, what used to be the notch is now an animated thing. So, because you have the camera and the microphone sensor or whatever up there. I think there's a couple other sensors that technically have like little tiny holes in the glass because they're doing something. But now they've surrounded that with an animated thing where that thing can like change in width, and they use it for notifications and stuff. So they're making use of the space, which is interesting enough. But they're selling this $1,000 phone on the concept of the, you know, the digital island is what they're calling it, you know. Yeah, and I have the phone and it's interesting enough, but I wouldn't call it any sort of life-changing feature. I'd much rather have emojis up there just from an entertainment perspective. Wouldn't that be great? Just use that space to just randomly like just show emojis during the day. Oh. Okay. So questions about those bitwise operators or how Booleans are actually stored under the hood. As good modern programmers, if I want to work with Booleans, I'll define it as a Boolean, and we're going to use trues and falses. Those are the words we're going to use. You know, the fact that we happen to know as academics that under the hood, a false is stored as a 0, and under the hood, if the compiler is doing it, a true is a 1, but the fact is anything non-zero is a true. Those are historical facts of how modern programming works. But modern programming has us dealing with trues and falses, and we can deal with trues and falses in these older languages like C++, and everything's fine. Just don't try to do math with Booleans, things like that. But just be aware that if you write a program and you think that what you wrote was fine, and you get instead of an error, you get some sort of number, you're like, what the heck is that? Let your mind immediately drift towards either I created a bitwise situation where I used a single Boolean operator instead of a double, you know, a single and instead of a double and, something like that. Or did I do some mathy stuff with a Boolean and this is C++ just rolling with the punches? Kind of let yourself drift there, because that's probably where your error came from. If you're getting an answer from something that logically shouldn't have an answer. All right, questions on that? Okay. So now that we have these Boolean operators under our in our toolbox, we talked about all our different primitive types. Here's our conversion stuff. Did we talk about if statements yet in terms of syntax? No.
Yeah.
Did we? Okay, well, we'll just show it on here. All right, so syntax for an if statement is if opening parenthesis, some Boolean expression, opening curly brace, closing curly brace. Optionally, we can have an else. So if this boils down to true, regardless of how complicated that Boolean expression looks. So remember, this guy is any expression that boils down to a single value of true or false. Yeah, I think last time we did an example with drinking, whether you can drink or not drink, right? Okay. So we can write if statements like this. and this else is not required. So we could do something like int a is equal to 5, int b is equal to 7. If a is greater than b, see out woot. And we can leave the else off. And since 5 is not greater than 7, this is false. Therefore, we will not do this. So the output of this program is literally nothing. Single this guy. See, error messages. So this is saying, hey, you've made a mistake. I did a single thing instead of a double thing. So make sure you read the error messages. All right, output of that program is nothing. I changed that to a 50. Now the output is woot. This allows us to ask questions. Remember, human beings solve problems by remembering things, asking questions, and then repetition. So let's talk about some repetition stuff. Loops in C++. We have let's call it three core kinds of loops. Modern C++ also has another loop called a for each loop, but don't worry about that right now. We have while loops. We have for loops. And we have do while loops. While loops and for loops are both what are called pre-check loops. I'll talk about what this means in a second. A do while loop is a post-check loop. Okay, loops use Boolean expressions just like if statements do. But an if statement allows us to ask a single question, and depending on whether it's true or false, we respond to it once. A loop allows us to ask Boolean expressions, so ask questions, but continue to do something as long as our answer remains true. All right. So a loop allows us to do repetition stuff still based on a question. When we say that while loops and for loops are pre-check loops, what we're talking about here is we will ask that question even the very first time. So the body of the loop executes 0 or more times. And it executes 0 or more times because that Boolean expression could be false the very first time through. For post-check loops, we actually check that Boolean expression after we execute the body. Therefore, post-check loops, the body of the loop executes at least one time. A majority of the time, you'll be using one of these loops. But every now and then, a loop like this might make sense. In fact, it's a very common situation when you have to type in your username or password, authentication. You have to read in the username and password and send it to the server at least one time, right? Most of our browsers and stuff store our username and password and send it for us, but something like that, we're going to say, what is your username? What is your password? Submit it. If it was false, ask them again. So the body still occurred one time. Go ahead. I think it might be difficult because they wouldn't necessarily know what results you were going to have. I suppose there might be a situation where it could make that jump, but I think generally a compiler is not going to know whether you got your username and password right ahead of time. Okay, so let's look at the syntax for these guys. And it's going to be very similar syntax to what we had for our if statements. So a while loop is the word while followed by a Boolean expression, opening curly brace, closing curly brace. Let's see. Statements. This stuff continue to happen as long as the Boolean expression remains true. So typically there is something inside this opening and closing parenthesis that makes a change to a variable that may impact the outcome of this Boolean expression the next time through. I'm going to show you an example here in a second. All right, so that's our while loop syntax. All right, so I'm going to say int count is equal to 0. And then we're going to say while count is less than 10. We're going to do something. We'll do a cout on count. And then we'll set count equal to count plus 1. So we have a variable called count. We're remembering something of type integer inside of a variable called count. We're starting it off at 0. Is 0 less than 10? It is. That's a true statement. So we will write out the current value of count, which is 0. And then we're going to modify the value of count to now be 1. Count is equal to whatever count used to be equal to, which was 0, plus 1. So now count is 1. Then we spin back up. We loop. Okay. Now we ask the question again. Is 1 less than 10? Yes, print out a 1, 1 becomes 2. Is 2 less than 10? Yes, print out a 2, 2 becomes 3, yada, yada, yada. Is 9 less than 10? Yes, print out a 9, 9 becomes 10. Loop back up. Is 10 less than 10? It's not. So we do not execute the body again. We fall past it. And now in this case, the program ends. So this is going to output to the screen 0 to 9. Make sense? Okay. So there's an example of a while loop. Now I'm going to write, now let's talk about what loops lend themselves to. Now I'm going to say you can solve any problem involving loops with any of these loops, but each of these loops kind of lend themselves to certain kinds of problems. For loops lend themselves to counting problems. Now we just did a counting problem. We used a while loop. Evidence that you can solve the problem with any of the loops. While loops lend themselves to problems where we do not know how many times we need to loop. Kind of, even though most of the time you use a while loop, you're going to be using it for counting type problems. A majority of the loops we ever write in code is going to be like, let's do something 5 times, 10 times, 100 times. Let's do something until some value reaches some constraint. Okay. But a while loop, a common, something we don't really use very often now, but would have been very common historically, is, have you ever seen some old program where you're out the command line that says press any key to continue? How long is it going to be until you press a key? Could be a half a second, could be forever, right? So that's a while loop. They pressed the key yet? Have they pressed the key yet? 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 Maybe there's some sort of built-in pause between checks, right? Instead of letting your computer go, hyper speed and just asking questions every, nanosecond. That would be an example of where maybe a while loop truly lends itself to that problem. But the way I'm going to show you here is that most of the time when we use while loops or for loops, when they're both pre-check loops, most of the time we're doing some sort of counting. For loops have the advantage in that variables become local variables, and I'll show you what I mean by that. What will the output of that program be now that I've added one more line? We've already seen the 0 through 9 in here, right? Go ahead. How much more? It'll print out the 10, right? So this will be 0 through 9 from this guy. Then the while loop we'll finally have is 10 less than 10. It's not. We'll fall past the while loop and we'll just stumble into the next line. What does the next line say to do? It says to print out the current value of count. Current value of count's 10. All right. And just as a quick example, we'll start here next time. A for loop lets you suck this variable into the header. So I'm going to say something like for int I is equal to 0, I is less than 10, I plus plus. We'll do a cout I. And notice that my incrementing of my value is now pulled into the header here. The definition of my variable is pulled into the header here, but that then has a consequence. It's going to scream at me. It's going to say, hey, I've never heard of a variable called I. Why not? I defined it right here because that variable I lived and died with that for loop. When that for loop ended, I is now gone. And when I try to print out I right here, it's going to say, look, I don't know what you're talking about. So we're going to start off next time talking about, it's going to do a start here, for loops and variable scope. All right, we'll have our next assignment assigned next class to do over the weekend using stuff we've learned up to that point. Sound good? Go ahead. Oh, I mean, always buy the best GPU if you're going to, I mean, I do a lot of VR. So with VR, the more horsepower you have in the graphics card, the better. So, but you got to look at that with a fine tooth comb, because when they say twice the power, it might just be in a very specific type of calculation. In many, many, many calculations, it might be equivalent, right? Well, yeah, but I mean, that's how it works. I mean, when do they actually start shipping? Yeah, and before the end of the year, maybe. Yeah. Hopefully we actually have availability of them. With cryptocurrency before we didn't, but now they're Ethereum can be mined without, it is mined without graphics cards now. So but yeah, I'll definitely have a machine with a 4090 Ti in it or something like that. But I mean, I drive a lot of VR. So oh, sure. Yeah. Well, but part of that price drop is because of the crypto thing. You couldn't even pick up a 3000 series card for 2 years. Well, it was because of the crypto people. They were mining with their GPUs and they ate them all up. And now what you have is an aftermarket for those 3000 series chips. And you want to be careful about them because if they came off of mining rigs, they've had quite a bit of wear and tear. They're probably fine, but you at least want to consider it. If you can spend 60, 70 bucks more and just get a new one off Amazon, do it.
I just bought a new one right now.
Yeah. What'd you get, a 3070? Okay. Yeah, but what games do you play? Yeah, so you're getting decent frames per second anyways. So if you had a 3090 Ti right now, you wouldn't notice a difference. Your monitor probably can't handle the output of it in terms of total frames, and your eyeballs certainly can't. Right. So with VR, the biggest thing is the more frames per second you can push or maintain the 120 hertz, the less motion sickness you might get if you're prone to motion sickness, that kind of stuff. But for traditional stuff, unless it's just, for bragging rights, like, okay, I can run Microsoft Word at 4,000 frames a second. Like, I don't need to, but I can. It's kind of like owning a McLaren, right? I mean, sure, I can go 300 miles an hour on port. You probably shouldn't, but you could. All right, what's up?
Where are we supposed to look for that?